Hello, Mr. Aaron, Mr. Ryan, are you right? Yeah. Okay, so we talk about the binary tree, the lowest common ancestor. Okay, we talk about that on day, I don't know, 100 days, something like that, of a binary tree or binary search tree. What's binary tree? What's binary tree and what's binary search tree?
Tree.
Okay, so which one of these is binary search tree? Let me just do another one. Which one is binary search tree and which one are...
The bottom one is binary search tree.
And all of these are binary tree, right?
Yeah.
Binary search tree, the nodes on the left are strictly smaller than the root. The nodes on the right are strictly bigger than the root. Okay, that's a tricky one. How about this one? Is this a binary search tree?
No.
Why is that? Because of what?
7 isn't strictly smaller than 7.
Excellent. Okay, so look at on the left hand side, these nodes need to be strictly smaller than 7, but at least 7. Yeah, even it's bigger than 6, but it's not strictly smaller than 7, right? Okay, so on day, I don't know, 114 probably, yeah, we talk about finding the lowest common ancestor of two given nodes. So we are given two nodes in the binary tree, right? And then we want to find out the lowest common ancestor. For example, like if we change this to 11. Right, if we given 7 and 9, what's the lowest common ancestor of 7 and 9? Ancestor, what's this mean? Ancestor, what's it mean in English? What's the opposite of ancestor?
I don't know what's the opposite.
Descendant?
Descendant.
Yeah, descendant. Yeah. Basically, this means their parents, parents of parents, parents of parents, parents, yeah? What's your lowest common ancestor? Eric here? Ryan here. What's their lowest common ancestor? Mommy and daddy here, right? Daddy? Yeah, remember the daddy's sister has a son. You met him before, right? Yeah. Look, daddy's sister. This is daddy, yeah? Daddy's sister.
That's not how to spell daddy.
Okay. Daddy's sister, you call, what do you call daddy's sister? Auntie? Auntie? Gugu. What do you call Gugu in English? Daddy's sister, so what do you call? Auntie.
I'm not sure.
You're not sure? Okay, so auntie, okay? Let's say auntie. Auntie. Okay? Auntie got a son, I don't know, called Zihan, okay? Yeah? So what's the common ancestor of Eric and Zihan? Daddy and auntie's parent. Grandma, you call Nai, right? Nai. Okay, Nai, okay. So, common ancestor. Yeah? So basically this question is asking what's the common node that has this descendant, has a descendant, yeah? That's what it means, okay? Do you get it? Yeah? Okay, another question. What's the common ancestor of 7 and 8? No, it's
11.
exactly. What's the common ancestor of 6 and 11? That's a tricky one. Guess.
11.
11, yes. So a node is an ancestor of itself and it's a descendant of itself, okay? That's the concept. Okay, so we talk about this lowest common ancestor in day 114 probably. And when we are talking about the binary tree, it could be a binary search tree, okay? Define f root p. On that day we talk about the recursion, yeah? So we want to find out, we are given this tree root, we want to find out the common ancestor of p and q. P and q are given in the binary tree, okay? So if not root, right, then we just return, okay? Return. If root dot value is in p dot value or q dot value, then we just return root, right? If p dot value and q dot value, right, is equals to root dot value. If the current given tree, the root is p and q, either of it, then we return it, right? Look, that's what it means. Look, right? P and q, and then this is also a root. Then as we talk about, a node is a common ancestor of itself, so we return root. Okay. F a root of left first of all, we find out the left tree, and next we find out the right tree. If we can't find if A is none or not A, right? If we can't find it on the left tree, look, here is the root, right? And then this is root on left, this is root on right. If we are trying to find the common ancestor in the left tree, if we can't find any, then it must be on the right, right? The same thing, if we're trying to find the common ancestor in the right tree, if we can't find it, where is it?
Left.
Left, yeah? So that's what we mean. Return, if A is none, return B. If B is none, return A, right? Okay. Right? Otherwise, if we can't find both, then there's only one possibility. The P must be on the left, Q must on the right, right? So in this case, which one is the common ancestor?
Root.
Root. Wow, excellent. You remember. Yeah. Okay. So this is previously we talked about recursion. So let's talk about it again. So first of all, if we solve this simple case, if P and Q or P or Q and P, if it's something like that, if the root is one of these, if P is the root, then we return P. If Q is the root, then we return Q, right? Because the node is a common ancestor of itself. If not, we're trying to find on the left tree, and we're trying to find on the right tree. If we can't find it on the left, if P and Q is not on the left, if P and Q in here, right, then it must be here, right? Look, that's what it means. If A is none on the left, we can't find it on the left, so it could be P and Q could be here, right? Or P and Q could be here. That's two possibilities. In either case, we return this one, right? So the same thing. If we can't find it on the right, it must be on the left. If we can't find both, right? If the common ancestor is not on the left tree and not on the right tree, so there's only one possibility. P and Q is on left and right separately. Then in this case, root is the common ancestor.
Yeah.
Okay, so let's recursion. Okay, how about if I'm telling you this is a binary search tree? Then that would be even simpler. Right, so look, 7, 6, 5, 6, 1, 5, 9, 8, 10. Right, so look, what's the common ancestor of 8 and 10? Here, if you look at here, both values, 8 and 10 is bigger than 7, so where is the common ancestor?
Right.
Right tree. Okay, where is the common ancestor of 5 and 6, 1, 5? It's, if you compare to this, on the left, right?
Yeah.
Then it must be okay. So then look, it's simple. If this tree is a binary search tree, we can just say, okay, if both nodes are smaller, then it must be on the left tree. If both nodes are bigger, then it must be on the right tree. Otherwise, which node? If one node is smaller, one node is bigger, which one is the common ancestor?
The root.
The root. Easy. The simple logic, right? Simple logic. So we can implement this. Before going to this, here, another way is to, okay, another way, I'm not going to write the code here. If this is a binary tree, now another way is to, look, we're given a root, right? So we can do this depth first search or breadth first search, passing to define depth first search, right? Root parent. We do this depth first search. If not root, return. And depth first search, root dot left. What's the parent of root dot left?
Root.
Root.
Middle root.
What's the parent of root dot right?
Root.
Yeah. Okay, then if we do this depth first search, then we can record this is a parent, yeah? Parent is a dictionary. Then we can say parent dictionary, the parent, root, the parent equals parent, right? What do we need this parent for? Look, given the root node, we can travel from parents to the kids. But we want it to in the reverse way, right? So we want to record the parent of each node. So given this, then we can do this P. We can do this P. How do we do this? We can travel backwards to the root. And then we remember the nodes in the table. So look at this one, 5. Okay, so I put it in the same table, right? 5, put it here. 6, put it here. 7, put it here. Okay, this is the table from travel from P upwards. Okay, and how about 8? Is A in scene? No, right? What's A's parent? 9. Is 9 in scene? No. What's 9's parent? 7. 7 is in scene, so 7 is the common ancestor. Okay, simple logic, right? So first of all, we do the depth search to remember the parents for each node, and then with P or Q, if we do this with P, we remember the nodes by going up, right? Going up here. And remember the nodes 5, 6, 7. And then now 8 or 10 here, right? Is 10 in sync? No. 10's parent 9. Yeah, because we have done this depth search. 9 in sync? No. 9's parent 7. 7 in sync, okay? So 7 is the lowest common ancestor. This is another way, okay? Coming back to this, okay? Binary search tree, okay? Easy. It will be easy. We can do this in two ways. Recursion and iterative. Recursion, easy, simple logic, okay? Define f root pq, okay? Look, if no root, return. Just to prevent the root is empty. Okay, now if p dot value is smaller than root dot value and q dot value is smaller than root dot value. If p and q both on the left hand side, then return f what? pq. Can you tell me? If p dot value is smaller than root, this is root, right? If p is on the left hand side, p is on the left hand side, so return f recursion. This is recursion. So what do we need here? Left, okay. And then again, if p dot value is bigger than root dot value and q dot value is bigger than root dot value, return calling itself root right and pq, yeah, easy. Root dot right here. Otherwise return root, yeah, perfect, yeah. Recursion, iterative, this simple. Iterate, this is recursion, and recursion calling itself here. Yeah. We navigated to root dot left or root dot right. We actually making the problem smaller, so we can try to solve a smaller problem, right? That's what the recursion for. Basically, at some point, you need to solve this problem. Otherwise, if the recursion don't end, what happens? It's just calling itself, and the computer just repeatedly calling itself without solving anything, alright? Yeah, remember the exclamation mark, right? Fn equals n times fn minus 1, right? Now fn minus 1 calling to n minus 1 times fn minus 2, right? Look at this one is n minus 1 times fn minus 2. So look, this keep recursing. But at some point we need to solve it when n equals 0. 0 exclamation is 1, right? Then once we get this 0 exclamation equals 1, then we go backwards to solve a bigger problem, recursion. But recursion has this problem that may sometimes if the recursion depth is too big, then we have this stack overflow, right? Stack overflow. Okay, so this one the same. Root, while root. This is the same, yeah. Look, if p dot value is smaller than root dot value, this is the same, basically copy it. But we are not returning. We go to the left. Root equals root dot left, right? If p dot value bigger than root dot value and q dot value bigger than root dot value. So in this case, what should we do? Root equals what? So now we are root here. We need to go to the right, right? Root equals root dot right. Otherwise, else we just break, and then at the end we just return root. Yeah. Okay. So these two are the same. Recursion, iterative. Okay. Okay. So to sum up, yeah, we talk about this problem in the early days, but on that day we talk about recursion to solving this problem on binary tree. But the title was incorrect at the time. The title was binary search tree. So with binary search tree, we can apply this simple approach. Yeah? The time complexity. If it is binary search tree, the time complexity is OH. H is the height of the binary search tree, right? Because every time we go one level. So the maximum distance we travel from the root to the leaf. Right? Every time we go down one level is height. In the worst case binary search tree, the height is the number of nodes, right? You know the binary search tree is degenerated like 1, 2, 3, 4. So it's basically a linked list. You know, it doesn't have two ways, right? So look at this binary search tree, right? Every time we can only go to the right, it's a linked list. Right? We're not using the characteristic of binary search tree. The left node are strictly because there's no left nodes. Okay. Also 1, 2, and then you go to the left, it will be 1.5. So every node has one kid. Then the height is equals to the number of nodes. The space convexity, this one we're not using any additional space. This one we're using recursion, but sometimes the recursion can be optimized. Okay, so if it's a binary tree, we can still use the iterative or recursion. Right? And we also talk about using the hash set. So basically, we perform the depth search, breadth search from the root to the kid. So we remember the parents of each node. Then from P or Q, we travel backwards to the root, and we remember we put those nodes. Yeah, we put those nodes in the hash set, right? And then we travel from the Q backwards again until it meets the first node that is already seen by key P, right? Yeah, that's what you do when you're trying to find the lowest common ancestor. Okay. Okay, so what have you learned today?
About the lowest common ancestor of a binary tree.
Binary search tree. Okay, so but how do we find the common ancestor, lowest common ancestor of binary search tree? So P and Q. So if they are both smaller than a root, then where do we find the lowest common ancestor? Left tree. And if it's all bigger than the root, right tree.
Right.
Otherwise, which one is the root? Okay, recursive. Oh, perfect. That's it for today. Bye bye.
Bye.
Bye.